Hi everyone, I'm Diego del Alamo. I'm a graduate student in Jens Meiler's lab, and I'll be walking you through the process of predicting the structure of a protein from scratch or de novo using an application in Rosetta called Abinitio Relax. If you have any questions about this tutorial, you can go ahead and email me at del.alamo@vanderbilt.edu. You can also access some of the resources available to you from the Meiler Lab website, which is linked right here. Before we jump into the tutorial, I'm just going to really quickly give an overview of how this method works and how you can modify it to fit your specific problem. So de novo protein folding is a very difficult problem in structural biology. Essentially, what we're trying to do is predict the structure of a protein from its primary sequence alone, so just the amino acids. This should only be done in cases where we don't have the structure of a homolog available or a closely related protein available, so we can't use homology modeling, and we also may not have any experimental data. Now, because of how challenging this problem is, it's really only suitable for small proteins. You can imagine that there are many possible configurations that a protein can be arranged in, even a 100 residue protein. And so you only really want to attempt to do this computationally if you have a small protein that you're interested in. For larger proteins, it just becomes impractical. So the protein we're going to be working on is T4 lysozyme, which is shown here on the left. You can also do this for small membrane proteins, alpha helical bundles. But once you get into larger membrane proteins such as rhodopsin, then it just becomes impractical. So we're going to work with T4 lysozyme, which is about 100 residues, and so we'll be able to get models that are actually pretty close to the native structure. Before we actually do the tutorial, though, and before we use Rosetta EPR, there's a little bit of pre-processing that needs to be done. So from our FASTA file, which contains the primary sequence, we can get a prediction of the secondary structure of this protein. Which regions are alpha helical, which regions are beta sheets, and so on. And from the secondary structure prediction and the FASTA file, we can then obtain these fragment files. And the fragment files are really the workhorse of this protocol. I'm going to talk in a little bit of detail about these fragment files on the next slide, but you're going to provide all of these files to a options file, which was mentioned probably in an earlier talk. And the options file is going to provide to Rosetta everything it needs to predict the structure of your protein. Now, if you already know the structure of your protein and you're just interested in benchmarking Rosetta Abinitio, you can also provide a PDB file with the native structure. And finally, if you have a little bit of experimental data that you want to use as folding constraints, then that can be provided as well. Now, these fragment files are so important that it's worth spending just a little bit of time talking about them. So the way Rosetta actually predicts the structure of a protein from scratch is pretty ingenious. You might not have the structure of the protein that you want, or even a related structure, but what you do have is a lot of unrelated proteins that have been determined structurally, experimentally, sometimes to very high resolution. And so what you're doing essentially is breaking up your protein into short stretches, generally 3 residues or 9 residues for historical reasons, and you're looking for parts of other proteins that match or are very similar to those 3 or 9 residue fragments. So you might have a part of your protein that's a methionine, followed by a valine, followed by an isoleucine. And there are many instances in the PDB where you have a methionine, followed by a valine, followed by an isoleucine. So you can just make a file containing every instance of those 3 residues in sequence, and then essentially try and fold your protein using that information. And what a fragment file is that exact process across the entire protein for 3 residue fragments and 9 residue fragments. Now, the process of fragment selection is generally guided by secondary structure prediction. It's guided by a few other things, and there is a publication at the end of this talk that you can follow that discusses this. But for the most part, experimental data is not going to factor into the process of picking fragments. The exception is NMR. If you have experimental data that gives you, for example, backbone dihedral angles, or you know a specific distance or something like that, then you can provide that information to the fragment picker, and it'll give you fragments that are consistent with that experimental data. But by and large, we're using just secondary structural information and the primary sequence of the protein to pick fragments. Now, how would you get fragments if you're interested in folding your own protein? Well, the easiest way, and the way that I prefer to use, is the Rosetta server, which is linked up here in the top right. If you're interested in getting fragments that way, you can just go and follow the link, and you just go to the fragment server and you provide your name, your email address if you have an academic email address, and your FASTA sequence, and you hit submit. That only works if you're an academic user. If you're not an academic user, then you have to look at other options. And two other options are this Perl script, which is here on the left, or the fragment picker application. And both of those ship with Rosetta and are available for you to use. The only thing that you have to do that's a little bit of work is you have to get all your dependencies in place, and that's something that someone can help you out with in the Meiler Lab, and we have resources to help you out with that. Now, the options file for Rosetta Abinitio is gigantic. And if you've ever used other programs for structural modeling from the command line, you know that it's quite common to provide a couple of flags just to say exactly what you want to do. But Rosetta Abinitio is, for me, and I've been doing this for a couple of years now, the program that requires the most flags, and it's not even close. So part of the options file is shown here, and this is basically going to contain all of the flags that you need to run your application. Just to very quickly breeze through this, we have all of the files that are going to be provided to Rosetta. If you have the native file, which in our case we do, and you provide the directory and file name, you provide the FASTA file, the fragment files, secondary structure prediction, parameters to guide the prediction for Abinitio, and then you provide this relax flag. And I'll talk a little bit about this at the end, but basically this is to get a full atom model out of your prediction. Otherwise, you end up with a coarse-grained centroid model, and generally you don't. You may want that, but you might not. Here's some more flags that are included in the options file. Probably the most important flag that's listed here is going to be this out nstruct flag over here. And this is going to tell Rosetta how many models to generate from this application. Now, because of the size of the search space for predicting a protein structure from scratch, you want to go with a large number, maybe at least 1,000, perhaps 10,000 models. Here we're just going to do one just for the purposes of this demonstration. But if you're doing this for a production run or something like that, you'll want to use a very large number and generate a ton of models. And then finally at the bottom you have the directory and file name for these models that are going to be generated. So if you have your FASTA file and you have your fragment files, how does that all come together to predict the structure of a protein? Well, the procedure is actually kind of underwhelming. So essentially what we're going to do is randomly insert a fragment in our protein. We're going to change the dihedral angles of a specific region of our protein to match that of a randomly chosen fragment. And then we're just going to evaluate the model, and see if there's an improvement in the score using an energy function, or if the score got worse. And if there is an improvement, then we accept that change. And if there's not, then we reject that change. And we're just going to repeat this process hundreds of thousands of times. And you can imagine that by doing this, and also by doing and by generating 1,000 models or 10,000 models, you can sample a gigantic number of configurations and hopefully end up at the lowest scoring configuration, which you expect would be the native-like configuration. Now, after doing this for a few 100,000 iterations, you'll end up with a centroid model or coarse-grained model. There are no side chains, and usually you want to get a full atom model from that. So I mentioned that there is this relax flag that we're going to be adding, and this is why we're adding this flag. This is going to add in the side chains, and it's going to do a full atom minimization and give you a structural model that has more detail than you would normally get if you omitted this flag. So here's a quick video that's demonstrating what de novo folding might look like on a small protein. The native model is shown in gray, and it's going to pop up occasionally for reference. This protocol always starts with what's called an extended chain configuration, where the model is fully splayed out, and the fragments are going to be inserted one at a time throughout this protein structure, and we're going to essentially cause the protein structure to collapse. And what this is going to do is that we're going to initially cover a lot of different conformations, but eventually settle into a local minimum. And then the moves that are going to be introduced, that are going to be accepted, are going to be quite small and are going to change from large global changes to smaller local changes. So that's what's being shown in this video, where of course we end up with a model that's very close to the native. Now, as I mentioned, that video is a little misleading because the vast majority of the time we don't get the native. We usually get some misfolded protein, and actually the proportion of models that are native-like is very small. One way to increase the number of models that's native-like is to provide experimental data, and the easiest way to do that is by using constraints. So here we have two examples for what kinds of constraints you can use. You have constraints that are obtained using electron paramagnetic resonance spectroscopy, or EPR, and then nuclear magnetic resonance spectroscopy, or NMR. And in both cases, we're first providing in our constraint file which atoms and which residues are being restrained, right? In this case, it's the C beta atom for each of these pairs of residues. And for EPR, we have a spline function that's specific for this technique. And then we provide the experimental distance value. And then for NMR, we have a bounded function with a lower and upper bound that's, again, specific for this experimental technique. Now, to introduce these experimental constraints to Rosetta, you just need to add a few options to your options file. So, of course, the file itself needs to be provided, and that's provided by this option here. And then you provide a weight, and for what we're doing, we're going to set the weight to 4, and that's been determined empirically to be the most effective way to incorporate these data. And then finally, we make a small modification to the protocol with this flag, the fold CST flag. Just to provide a little bit more information about what these restraints are, the Rosetta EPR module, which was developed in Jens's lab, basically converts distance data obtained between paramagnetic spin labels, which are shown up here in the top left, into restraints between backbone atoms. Now, in general, the tendency for these spin labels is to be slightly farther apart than the backbone atoms that they're linked to. And so for this reason, we actually use a spline function, which is shown on the bottom, to translate those distance values into backbone restraints. So this has been, again, published out of Jens's lab in a series of publications, and it's actually very effective at reducing the number of misfolded models that end up being generated using Abinitio. Another option, which is relatively fresh and published last year, is Rosetta NMR. And unlike EPR, there are many different ways of incorporating NMR data into Rosetta Abinitio folding. I mentioned that you can use NMR data to actually pick backbone fragments using chemical shift data. But you can also just use distance restraints similar to what was used for EPR. So these can be short distances, such as those obtained using NOEs, but you can also use other experimental data obtained using NMR that may provide longer distance values. Finally, something that's become popular in recent years is to use residue-residue coevolutionary couplings that are predicted from large multiple sequence alignments. And in this case, since these predicted contacts are not necessarily guaranteed, right? They're predicted from bioinformatics data. There is a chance that the restraints are false positives. They are just artifacts of, the data that's being provided. And so the constraints themselves are actually set up to reflect that, and to reflect the possibility that, a predicted contact is not actually real. But for the most part, the majority of the contacts that are predicted to happen do in fact happen. So you can get a constraints file from the Gremlin server, which is linked up here in the top left and shown on this slide. And actually this is convenient because it will generate the constraints file for you, and then you can just download it and use it immediately without any additional processing. But at the end of the day, regardless of where these constraints come from, they're all going to be passed the same way to the Rosetta EPR protocol, which is as a additional score term when you're evaluating the model. So you can have a move, for example, a fragment insertion that would otherwise be rejected by EPR, but since it satisfies a constraint, perhaps it's instead accepted. And so depending on the number of constraints that you have and the quality of those constraints, you might end up with a larger pool of native-like models than you would if you did not include those constraints. Now, again, with the exception of NMR, which can be used to generate fragment files, the actual Monte Carlo moves that are being introduced don't change. So you still sample the same way, you're just scoring them differently. And then additionally, you can provide constraints during the relax step, which we're going to do. And then this way it'll kind of settle into a full atom minimum that is more consistent with those constraints than if you did not include them during minimization. Now, as a last step, you have to generate many hundreds of models, perhaps thousands of models. How are you supposed to analyze these data? Now, the most effective way to do that is to get the root mean squared deviation of your models, which is shown here on the x-axis, and then to plot that against the score on the y-axis. And if you have a native model, right, if you're doing this for benchmarking, which we are, then you can just get the root mean squared deviation to the native model and then get an idea of how many models were close, how close were they, do they score well. But even if you don't have the native model, this tool is still useful. You can get the root mean squared deviation to the lowest scoring model, and then after calculating the RMSD this way, you can get an idea of how much the models you generated converge upon this one minimum, right? How many low-scoring models are there that are similar to each other? And depending on how much sampling you did and how many models you end up with, you can actually identify with some confidence the native conformation of a protein if, all of your low-scoring models look very similar to one another. Personally, I have a preference for just opening up these models in PyMol and seeing them compared to one another. And then that gives you just a very good idea of how similar these models are, how different they are. Are there regions of consensus? Are there regions of divergence? And so on and so forth. So that is my preference, and I would encourage you to take a look at the data that way as well. So to very briefly conclude this talk, AbinitioRolax is a useful protocol for predicting small proteins. Experimental data can be incorporated relatively easily, and this will lead to an improvement in the number of native-like protein structures you end up with. And this protocol has been used extensively for over 2 decades now, and so there are tons of papers covering it and building upon it and highlighting improvements to the protocol. And I would encourage you to check out some of them. I've listed a few here. I would also encourage you all to read the fragment picker paper, because that has a lot of details as to how you can improve your prediction outcomes just by changing which fragments you're going for.